Hello YouTube viewers, welcome to my show Science Thursday. In today's episode we're gonna take a closer look at electrical grid. So let's dive right into it. Now first thing you have to understand, electrical grid is the largest creation ever done by man. Like this thing is so big that Large Hadron Collider looks like a toy. It's very important because it is modern lifeline. Like if electricity goes, everybody goes. We have to have electricity. It's not a luxury. You have to have it for water, you have to have it for food, you have to have it. It's absolute. And there are a lot of parts into it. There is power line, there's substation, there is plug at your home. So this is at this point in time largest creation there is. And on top of that, you also have to understand this is so good that it is practically invisible to us. You don't think about electricity. If I asked you where is your nearest substation or which substation you are getting electricity from, you may not even know it. And that's okay. Like electricity is invisible, so it's supposed to be invisible to us. Like you just plug your things into wall and that's it. Voila, things work. So it is a very large creation and yet it's invisible to us. But then you have to come to certain understanding. There are a lot of problems inherent to it. Now the first problem you have to understand, it's very instant, as in it's almost at the light speed. Now of course it's not traveling at the light speed. You can send signal to a fiber optic that will travel faster, but it is almost at the same speed. So that inherently means, let's say you have a water canal, let's say you have a canal from one state to going to another state. Let's say flooding occurs here, you can call them, warn them that flooding is going to happen, and they can react to it. Now of course they will only get, depending on distance, few hours to few minutes, but they will get some warning. In case of electricity, it's instantaneous. So if fault occurs, let's say in a power plant or in a power transfer line, it's done. It instantaneously affects everything in the grid. There is no else if here. It's instant. And on top of that, the load, basically whatever people are consuming, it's not constant. That fluctuates throughout the day, every day, 24 into 7 into 365 into as long as the grid is active. So that also creates a problem, that you simply can't say, okay, power plant, give me 60 megawatt per hour. That's it. You won't be like that. You could do like, okay, 60 megawatt right now, give me 1000 megawatt in afternoon, then give me like 1500 because there is a sports match going on, everybody is turning on their TV at the same time. Things of that nature happen. That fluctuation creates an issue. On top of that, we don't have any power storage that is big enough for a grid, because you have to understand, we are talking about gigawatts here and hundreds and thousands of them, not even one or two, hundreds and thousands of them. So it's very big. So power storage we can have on a small scale. You can check my video about power storage, grid scale power storage, but suffice to say it's very small. And the equipment that we use, basically anything that you see, your power plug or things of this nature, basically these are very intolerant. Basically they will not tolerate anything other than their specified limit. So for example, like this is a AC motor and it flat out says 220 volt to 230 volt. What does that mean? Does that mean it runs on 12 voltage? No. Every electrical equipment that is created must have tolerance of plus and minus 5 to 10%. It's required by the law of so everything. So let's say you buy an adapter, there will be tiny print here and you can read it. I would urge you to do so. Like look around you, you will have a mobile adapter or something laying around and you can easily read it. What does it say? So it will say things of like 50 to 60, like these things are very tolerant. Everything other than this is very intolerant. So basically anything that is running directly, it's very intolerant. Your light bulb, yeah, it's gonna fry if you change anything you change into it will fry. You have water pumps, that's the very crucial lifeline. You change the voltage on that, yeah, that's gonna burn up. You have ceiling fans, you have basically normal air condition. The advanced air condition can handle a bit more because they are running on DC, that BLDC motors or inverter driven, they can handle a bit more fluctuation. But anything normal or ubiquitously use, anything that is running directly has very low tolerance. So that creates a problem. Any equipment you have has 10% plus and minus, but how the heck a power plant supposed to handle that? So power plant, understand, the power plant job is to make sure you get power, make sure you get the power constantly, and there is any fluctuation that happens will affect anything that is connected to the grid, and it is instantaneous. So it must apply a brake, basically circuit breaker, before that instantaneous effect becomes too difficult to manage. So it is very problematic to handle. Like it is a big thing and it is a very problematic. So On top of that, you have to understand the power generation aspect of it. Now, if you simplify it, like you remove coal, you remove hydro dam, you remove nuclear power plant, you remove everything there is, then you ask the question, where does the power come from? The answer would be spinning mass. So basically, no matter what you have in terms of power generation, other than solar power, everything else is spinning something, be it turbine, be it a generator, whatever it is, there is always something spinning that is creating your power. Now, on top of that, whatever power plant you have, coal power plant, hydro power plant, whatever, they must provide constant. Now, the load changes, but what do they must make sure that it is constant? They have to make sure the RPM, as in the frequency that is coming out of your power plant, be it 60 Hz, be it 50 Hz, it must remain that no matter what happens. Either it's better to cut it off than to like send incorrect frequency. Now, you might be like, okay, 50 to 60 Hz is not that far apart. It's not like 110 volt to 220 volt. It's not twice gap. The gap is very little. But you have to understand, the lower the frequency, as in let's say 50 Hz, the transformer size becomes bigger. However, your transmission efficiency becomes higher. So at lower frequency, as in 50 Hz, you can send power to further distance, and it also reduces skin effect in conductors. So it's quite a good. But let's say you send 60 Hz, the power simply won't get to the target. Now, if you have 60 Hz and you send 50 Hz, the transformer will simply blow up. So in those sort of scenario, you must understand the RPM, basically the spinning mass, must remain constant. That is the job of power plant. If you go into power plant and you see 10,000 equipments that are like monitoring this, monitoring that, all of them are doing one thing, making sure the RPM remain constant. The frequency must not change. Like voltage changes, your equipment can tolerate. Frequency change, yeah, it's gonna catch on fire. So this is the aspect of power generation. So we have a lot of issue. We have power generation with using spinning mass. Power generation using spinning mass. Then question becomes how we are handling it. Like, of course, there are a lot of problems. Then how we are handling it. Now, the stability of your grid comes from two aspects. The first aspect is voltage must not change, because it does not matter where you have, let's say, basically big plug drawing something big, let's say a water pump or something small. They are both supposed to run on 210 volts, like in case of India. So the voltage must not go down. It does not matter you are running a CFL or running a LED light. The voltage must remain the same. Now, to handle that, to make sure the voltage does not change, we use something like this. Basically, it's what we call on-load tap changer. You can check my video about large transformer, because this is where they are. They are generally not on your home substation near you. They are generally on big substation. They make sure the voltage always remain within a tolerance. Basically, they make sure the fluctuation is below 10%. to make sure that your building does not catch on fire because of electrical faults. So this is how we maintain the voltage aspect of it, because we can change the step down or step up the voltage using transformer. So that problem is very easy to take care of. Then the question becomes, how the heck we maintain the frequency? Now frequency, you have to understand, frequency comes from rotating thing. Now because it's rotating, it has what we call inertia. Now as in, like, if you have seen any generator, you must see a very giant flywheel into that acts as a dampener, a buffer. Let's say there is a generator, let's say a power plant, big power plant has a generator which has a turbine that is rotating and providing your power. Awesome, everything is awesome at that. Now here's the deal. Let's say that power plant turbine is rated for 500 megawatts, but you put a spike load on it that is 10 megawatt extra. Now what will happen? Now it will slow down, but here's the deal. But because of the mass, because of the fact that it is hundreds of tons, it will not slow down instantly. It will take few seconds to slow down. Now that few seconds is long enough for computer to detect, okay, my RPM is going down. Basically the frequency hasn't started to go down, but like computer will detect it. Okay, like my frequency, instead of being, let's say, 60 hertz, is becoming 59.993. Computer detects it, increases the valve, like opens the valve open, and then valve circuit sends the signal to coal power plant, hey, burn more coal to give me more steam. Or in case of hydro dam, open the valve for water flow. So this is how we handle it. So voltage is handled on a substation level by using tap changer. The frequency that must not change is taken care by spinning mass. Now if you say, people say a lot of issue comes from integrating renewable energy into the grid, this is what they are referring to. Voltage is very easy to maintain, that's not an issue. We have the technology to do that. However, because renewables generally don't have anything spinning, let's say in case of wind turbine or in case of solar power plant, in solar power plant there is nothing. So let's say you sent a wrong signal. Let's say the power plant, for some reason, it does happen times and time again, the frequency do change. They try to combat it, but let's say something happened. Let's say for 5 minutes the frequency went down. The solar power plant will not notice it because it is directly reacting to the basically it's reacting to the grid. So grid goes down or goes bad, the solar power plant will make sure that it remains permanently bad. It will destroy the grid. That's why people are very afraid of the fact putting non-spinning mass into basically our grid. Then you will ask me like, okay, doesn't wind turbine have a spinning mass? Now that's absolutely true, but you have to understand it's spinning based on wind. You do not control the wind. So generally many times they have flat out DC generator and then they convert to AC, so they can control the frequency absolutely. And other times they use what we call slip induction generators. So that way, if the frequency goes higher, it will take that away, convert that DC, then make it to AC again, and then sell it to you. So you can understand, because renewables cannot negotiate. Renewables, this problem in renewables is absolute. You cannot bypass this. A solar power plant cannot tell you like, okay, 60 hertz will be maintained. If you give solar power plant, let's say for some reason some fault occurred and the frequency going into solar power plant, that's why they say grid tie inverters. That grid tie inverter detected, let's say it's going to, let's say 58 hertz frequency, it will give out 58 hertz frequency. Now of course modern inverters have fail-safe. If they detect the frequency is going below, let's say few percent plus and minus, it will cut the signal, because of course people learned that the hard way, that things catch on fire when you frequency change. So this is how we are stabilizing our grid as of now. We have tap changes to handle the voltage, we have giant spinning mass to give us time. Basically, now you would be like, okay, what happens if we overload it? Let's say a power plant can handle 10 megawatt plus minus, okay, awesome, but what do we do when let's say a power plant is getting 100 megawatt spike? That's the time when circuit breaker comes in. That's the time when you lose your power. That's why like cutout, blackouts, those sort of thing happens when spinning mass is no longer capable of handling. Because it does not mean like, let's say it is spinning and this is generating 100 megawatt. It does not mean you can put 10,000 megawatt load into this and it will keep spinning. It will slow down considerably, and it will still give your computer enough time, enough warning that computer will trigger circuit breakers. Instead of like, it will detect it like, okay, slowing down is happening way too much. Like, instead of frequency going from 60 hertz to 59.993 is going 58, it directly dropped one whole cycle. It's like, okay, it's too much of spike, trigger the failsafe. So this is how we maintain the stability of our grid as of now, as I talk to you. Then the question becomes like, all of these things are happening, these things are relying on communication, because your substation must talk to the power plant, hey, we need more power, hey, we need less power. Because if you don't do this, you are only reliant on the fact that power plant is constant. Now that's a good thing, but that's also a bad thing, because power plant cannot be absolutely constant, and on top of that your load is not constant. So there is a communication. So if you see something like this, a big hanging mass on old substation, they are what we call wave trap. So in earlier days we used to use what we call power line communication. Basically that high voltage line that goes to substation, that itself used to carry signal. So basically there was a dial-up kind of connection, 9 kbps connection. It was telling like, okay, my load is 80 megawatt, 90 megawatt. Using that information, computers were controlling the output. So if the output goes too much, then the signal will come from power plant, hey, you are overloading, either trigger let's say cut out some blocks of electricity or flat out disconnect permanently. So the communication is very important. Now of course this was not very good, but it did have the aspect that it was cheap, because you already had the power line, and this wave traps were not that ludicrously expensive. So after wave trap, then we created what we call optical communication. So now you have complete optical line. So power plant and basically substation, they are in contact 24/7/365 with very high bandwidth, so they can communicate very well. And this also allows for large power plants to be connected to a central node. This allows, like, let's say 500 megawatt is like, overload, you have to cut power, but let's say you are communicating with other, you may find, hey, that power plant is overproducing 100 and it has to tone down. Rather than toning it down, you're like, okay, sell that electricity here. All this trading that is going on, it's almost like a stock market. So that is happening because of communication. So communication is crucial. You cannot have a national grid without communication. You must have good communication. Without communication, you cannot maintain your frequency. Without communication, you cannot maintain your voltage. And let's not even talk about the dangers that will create. So communication is the key. If communication works, your grid is safe. If your communication goes down, you dead. So, and on top of that, so our grid right now, as I talk to you, even any grid going back as 1980s, they are very smart. They talk to each other, they understand the load, they handle the situation, they predict also. There are a lot of graphing meters that were used to, graph out the load, and mathematicians used to study the loads and all that. Then they predicted, like, okay, on Sunday, I think Sunday afternoon there is a lot of power demand, and in summer vacation the power demand goes down because a lot of schools are closed and people are away for trips and all that. So there were people whose job was that. Now it's done by computer, because now we have a better computer, B, larger data set because of optical fiber. So our grid is very smart, and you can check the video down below that I have provided about a smart grid. That's a UK smart grid. but it will become smarter once we implement what we call smart grid. Now you can check my video about smart grid here. So basically this is on your home level. I talked to all the communication that I was talking about is happening between power plant and substation. It's not reaching the last mile, it's not reaching you. Basically you have no idea whether a power plant is working properly or not. This smart grid will allow you to do that. Basically smart grid will allow, hey, right now there is peak demand, would you like to tone down your power requirement? And you're like, you may do it or you may not do it, but here's the deal. Let's say you have smart equipment, let's say your washing machine is smart, let's say your water heater is smart, your air conditioner is smart. They will be like, okay, let's chill down, because they know the smart meter has to do this, because if let's say power demand keeps going up and up and up, you will have a power cut. That's not good for anyone. So it will be like, okay, let's I think you are in a room and you are working, like, you need air conditioning, but I think I can postpone the washing machine. So they will save off a little bit of spike. Now you might be like, okay, that would not make much of a difference. Yes, if you are talking about one home, but if every home starts to do that, the power demand can be handled very, very effectively. This is why communication is the key. You want to have greener environment, you want to have a absolute environment where you can, be reliable on electricity, you have to have smart grid. Basically smart grid is a bad term. I like the idea of smarter grid, because our grid is very smart. And when I talk about frequency response, you have to understand, when somebody is talking about, let's say 60 hertz, it never even goes down to, let's say 60 hertz is there, it will never go down to 58. It's that good. There are that many people working on it to make sure before it goes to that low, they will cut the power. They will make sure that you, under no circumstances, you get power that is dirty, basically dirty power. You don't want to get dirty power. Your equipment will not like it. Unless you are a DC converter, basically like a charger. Charger will work, no problem. So this was my presentation on basically grid, our electrical grid. I hope you liked it, learned from it. In that case, please click the ad that are shown in this video, like the video. If you didn't like it, don't worry about it, you can press dislike. I would urge you to press it twice to show me your extra disappointment, and please leave a comment. I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.